if you are wondering how Raoul overnight got so very much younger and so very more beautiful, it's because he's stranded in Frankfurt due to fires and to the wind. So Druba has kindly accepted to step in. So thank you very much for that. So Druba was Raoul's student.
Yes.
Did his PhD with him, and then he joined the Uriel Frisch as a postdoc in Nice, and then in Queen Mary, and since he's been in Nordita. So it's first time for you in the
Absolutely, yes.
Very happy to have you. And we expect great things. If I remember correctly, you were a Taylor Swift fan, is it?
Oh my God. Okay, we will come back to that.
Please.
Thank you. Thank you. So, right. So, I'm Mikro, but everyone calls me Dhruba, Dhrubo. It's okay. You can call me anything practically, and it's okay. So I work in Nordita, Stockholm. I have been there for a long time. And I work on many different problems. I have worked on astrophysical problems. I have worked on problems in biology. I still do in, say, microscale cells and even smaller vesicles. I have worked on astrophysical plasma, but never on fusion plasma. And so I'm very happy to be here. And last year, I met Patrick and Guillaume and several other people here in Cambridge. And then when Guillaume invited me, he said, there is a festival in south of France. So I thought he meant this one. But it is a bit okay, but still, I'm very happy to be here, nevertheless. So, okay, let's start at the beginning. So I will talk about elastic turbulence. But before we get into elastic turbulence, let's start with turbulence. So what is the turbulence problem? See, there are many, if you ask popular science, they would say, Feynman said turbulence is the last unsolved problem in classical physics. I don't know if Feynman actually said that. But it's not clear that there is a turbulence problem. There is a mathematician's turbulence problem, which will give you $1 million, which is solving about the singularity of the Navier-Stokes equation. There is what I like to call engineer's turbulence problem, which has to do with stability, the kind of thing that Mike Graham talked about. This is how turbulence comes in, the scenario by which it appears, and the beautiful patterns that come out of it, and so on. And there is the other turbulence problem, which is about statistics. What are the statistical properties of turbulent flow? And there is, of course, I mean, there has always been turbulence kind of two camps, the structure people and the statistics people. And it's not clear always that one has to say something about the other. But this is the dichotomy we live in. So I am going to focus on the statistics part. Okay. So about the statistics part, we start with statistically homogeneous and isotropic turbulence. So these days, homogeneous and isotropic turbulence has been shortened to HIT. And if it is statistical, then it's statistically homogeneous and isotropic turbulence, but don't look for the acronym of that. So there are, as you know, oh, by the way, other thing, I forgot to say this. I thought of saying this. So after my talk in Cambridge, when I met several people here, they all said, oh, you gave such a nice talk. And then when I talked to them, I remembered that only thing they remembered from the talk was the jokes. So this talk, I have decided no jokes at all. So, okay. So this is what I like calling 3 pillars of turbulence research and the statistical turbulence research. There is Kolmogorov, there is Richardson, and there is G.I. Taylor. So Kolmogorov, I think everyone knows about Kolmogorov results here. The idea is that in homogeneous and isotropic turbulence, you get an energy spectra, which is k to the minus 5/3 in the inertial ranges. This exponent, which is minus 5/3, is not exact. There is a little bit of correction to that because of intermittency, which I will come to. But the broad picture is that there is large-scale behavior, which depends on how you are forcing the system. There is small-scale behavior, which is controlled by viscosity. There is intermediate inertial scale, which is supposed to be universal in the sense that the exponents are universal. It may be that the amplitude of the scaling is not universal. And that's whole debate about whether there is a Kolmogorov constant or not, but sidestep that for the moment. Then there is Richardson result, which says that how two particles separate in a turbulent flow. And then there is G.I. Taylor's result, that if you look at a single particle, how it diffuses in the flow. The last one has to do with mixing in turbulent flows. So just to be an outset, I want to say there are two important features when they appear, I will call a flow turbulent. One of them is that there need to be a power law behavior of energy spectra, at least over a certain range. And second, the flow must be mixing. Okay. Please don't hesitate to ask any question. Okay, that's the homogeneous and isotropic turbulence. But then turbulence got diversified. There are many, many kinds of turbulence. The passive scalar turbulence connected to the Kraichmann model you may have heard of. That's the only problem we can solve. Then the weak wave turbulence that Michel talked about yesterday. There is 2D turbulence, there is compressible turbulence, stratified turbulence that Michel talked about, MHD turbulence that a lot of people here know and worked on, polymeric turbulence that Mike Graham talked about, turbulent convection. And I haven't put plasma turbulence in this because I think that's a huge beast just by itself. It's practically the Godzilla of the problem. But leaving that aside, all of these ones, the key problem they are trying to understand, the key feature they are trying to solve is the nonlinear advection. That is the devil in the problem. We really don't know how to deal with it. So we have different approximations, huge simulation, and various ways to deal with it. But all of them are nonlinear advection plus something, except the Kraichmann model where the nonlinear advection itself is modeled. That's why I have it in a different color. Otherwise, this is the big picture. But what about turbulence without turbulence? Can you have a turbulent flow where the nonlinear advection is absent, subdominant, or less important? There are other nonlinearities that can be present. But these two features need to be there, the power law spectrum for velocity and mixing. So there could be other sources of nonlinearity coming into the problem. And obvious candidates are elastic nonlinearities. So you remember Prasad talked about pseudo-turbulence. Pseudo-turbulence appears at small scales, large Fourier modes. So you could say if you think of a scale-dependent Reynolds number, then those scales don't have a large Reynolds number. They are about order 1. But you get a power law behavior there, and that is coming because of bubbles. So not because of the advective nonlinearity, but because of the bubbles. And the other one that I will talk about is elastic turbulence, which appears at small or zero Reynolds number and appears because of elasticity of polymers. Okay, so that's the problem I am going to talk about. And for last 5 years or more, I have been interested in this aspect of turbulence without turbulence. Because clearly the advective nonlinearity is terribly hard. Maybe something else is easier. Yes, please.
So what you call turbulence without turbulence is nonlinear advection without the other features of turbulence.
The other way around, no nonlinear advection, but some other nonlinearity.
Okay.
These are all small Reynolds number behavior or even zero Reynolds number behavior. So anyone knows hard about microfluidics here? But among the students, so see, I'm addressing the students. No, none of you heard about microfluidics. So these are very thin channels, which is the amount of liquid is in nanoliter because that's volume. And the typical dimensions are micrometers. And you can build practically a chemical reaction in a small chip. You can say one chemical coming from here, coming from there, they meet, go into, meet some other chemical, and I can build whole chemistry in a small chip. And these are extremely useful. You can, for example, if you take it somewhere, you ask someone to spit in it, and you find out that they have a disease. And they are very happy to know about it, presumably. Anyhow, so, but one of the problems in microfluidics is, see, if someone over there is wearing a perfume, I can smell it. I can smell it pretty quickly. But if you look at the diffusivity of a perfume molecule, that is actually very, very small. If it was diffusing only by the diffusivity of a molecule, then it would take a day to smell someone's perfume across the room. What happens is there is mixing because of the turbulence in the room. That's what actually makes us smell things, well, good and bad things. But in a microfluidics, because the Reynolds number is very small, 10 to the minus 4, let's say, there is no mixing. That means reaction happens extremely slowly. So if you could speed up this in microfluidics, that would be a huge improvement. So if there are other nonlinearities in small Reynolds number that could give you mixing, that would be a wonderful thing to have. Okay. Okay, I have distracted a bit, but before we go into that, before we go into look at elastic turbulence, let's have a clear idea of what I mean by homogeneous isotropic turbulence. So it is characterized by what are called structure functions. So you look at 2 points, you look at the velocity difference between 2 points, and you take it to the power p and you average. That's your structure function of order p. And then you look at the scaling behavior of that structure function and you get an exponent. So if you were Kolmogorov and you wanted to make a dimensional theory, you can show, well, before dimensional theory, you can show that the second order structure function, S2, is the exact Fourier transform of the energy spectra. The energy spectra has a scaling of k to the minus 5/3. The second order structure function has a scaling of r to the plus 2/3. And any pth order structure function in the Kolmogorov theory has a scaling exponent of p/3. So here I am plotting the scaling exponents as a function of the order p, and the straight line is p/3. That's the Kolmogorov results, which you can prove by dimensional arguments. So how many of you know can prove Kolmogorov? None of you have been exposed to Kolmogorov? Okay, we can deal with that today later. Okay, so that's Kolmogorov for you. But when you actually measured these exponents, they are not exactly the Kolmogorov exponents. Small exponents, small ordered exponents are slightly different. P equal to 3 is exactly 1. That's the only one exact result in turbulence. And P higher than 3 are actually smaller than the Kolmogorov value. And the difference is called delta P. And this is a behavior that is called intermittency or multifractality. Let's not go into the regime where you say why it is called multifractal, but I can quickly tell you why it is called intermittent. The word intermittent means something that happens now and then gone, right? There is intermittent rain and so on. So if you have a statistics of Gaussian, let's say, then large fluctuations are extremely rare, right? They're exponential squared times rare. But if you have probability distributions which falls off much slower than Gaussian, then you have a much higher probability of large fluctuations. These are intermittent problems. So what happening in turbulence is that you can actually have very large fluctuations, much more probable than what would have happened if the statistics had been Gaussian. So that's what intermittency means. So if you start with the Navier-Stokes equation, do a systematic calculation, find the exponents delta P from that, you have solved the physicist turbulence problem. You will not get $1 million, but you will get much more than $1 million. This we don't know how to do. But this program has been successfully implemented for what is called the Kraichnan model of passive scalar, where you can actually find these exponents delta P from theory. That's an amazing result. Okay, so stepping that aside, you can see these results from the latest simulation. These are from numerical simulations from 2023. And these are the largest simulations of turbulence that I know. So we come to elastic turbulence. And the hero of elastic turbulence is this guy, Victor Steinberg. So see, many subjects that we talk about, it's very difficult to say, oh, that guy at that point invented this. In this case, you can. The elastic turbulence was literally invented by this paper in 2000. Now, of course, as one of my people I knew in Nice, Misha Blanc used to say, anything that is worth discovering has always been discovered before. So in that sense, this is not completely true. There were indications of this from early works of Schachfeld, who showed that if you go to the elastic regime at small Reynolds number, there are new instabilities. So it is likely that there will be turbulence. But turbulence in the sense of power law spectra, I believe this was the first. Right. So this, it's not that it came out of nowhere, but it, to me, actually it did, because I was just a PhD student there. And it was amazing to me. So there were two papers, one after another, where there is elastic turbulence in polymeric flows and then mixing in this low Reynolds number by polymer additive. These two kind of setups, one is like a Taylor-Couette problem, but at very small scale. And the other one is like this serpentine channel. And what you find, seeing these things, the spectra was measured by putting a single probe into the problem and finding out the velocity fluctuations. So of course, you students you are born in the time of plenty. You are in turbulent summer, because you can visualize whole flows. If you remember history, for a long, long time in a turbulent flow, you will put a single probe and you will get a time series, and that's all you will have. And you will basically have just one component of velocity. If you want several components, you have to do tricky probes. And things were not so nice then. So in this problem, for quite some time, there was a results which you only knew as a time series of velocity field at a single point. So you Fourier transform that for spectra, you get a frequency. And here you get a power law, and the exponent is presumably minus 3.5. Okay? Not over a very large range. And I should also tell you, many things look like power law once plotted in log. Okay? This is, older people know very well that when you see a power law, you should be careful. And you can play with this. You can plot different functions, plot a power law, add an exponential to it, and then plot it in different log scales. You will see that many things can be, once tortured, many things give rise to power laws. So be very careful of power laws and more careful of the exponents that come out of it. And you should always put error bars in the exponents that you find. Okay, but that's not so easy. If you look at this, so one of the ways you could try to make an error bar is to say, I calculate local slope. But if you look at the plot, you see the local slope will actually fluctuate quite a lot. Okay, anyhow, this is the beginning of elastic turbulence. So now I am going to draw kind of a phase diagram, very crude one, in Reynolds number and Deborah number. So Deborah number is the time scale of the polymer divided by the time scale of the fluid. At this moment, I pause and remind you of everything that Michael said. And that was a great thing for me. Otherwise, I would have to do all of that. So a polymer, you can think of it like a bead on a spring. But this spring is a overdamped spring. So you pull the polymer out, it just goes back. It doesn't overshoot. Okay. And the time scale of this is the tau p. Now, a polymer typically is made out of monomers. So if there is nothing acting on it, that monomer will coil up like almost a spherical shape. And the end-to-end distance will be like the square root of the number of monomers. When you pull it out, the end-to-end distance can be like the number of monomer. So the difference between a coiled up monomer and a stretched monomer is from square root of n to n. And for a large n, that can be quite a large distance. This is the clue to all the problems of polymers in flows. They stretch and then they make a mess. Now, as you go to Deborah number, higher and higher Deborah number, you could say things are more elastic. So if you are in small Reynolds number and small Deborah number, you get laminar flows. The part of this phase diagram that we know best is the horizontal part. So you stay at 0 or small Reynolds Deborah number, go horizontally, laminar becomes turbulence through many instabilities, and eventually you will get k to the minus 5/3. From there, if you start increase Deborah number, you are now going into the regime of polymeric turbulence. So Mike talked about polymeric turbulence, more of what is happening in these parts, where there are instabilities that are appearing, structures appearing. I am talking about very high Reynolds numbers, where I am looking at the homogeneous and isotropic case. And this is not what we will talk about today. So leave that. we stay at small Reynolds number and we go up the Deborah number, new kind of instabilities come in. And this is a very rich place of research. But what I'm looking at is when you go past those instabilities and get to the elastic turbulence, and I have a plot with a slope of k to the minus 4. Okay. Victor's early result was k to the minus 3.5. I am now plotting k to the minus 4, but this is what I will discuss for a little bit of time. Okay, how much time do I have?
That k to the minus 4 spectrum is a spectrum of what?
I will come to that. That's the core of what I'm going to discuss. Excellent, thank you. How much time do I have? Good. Okay. So this is a result of the spectrum of elastic turbulence obtained over time. So you start with 2000 and you have just this one number from Victor. Now you see two colors, blue and, well, orange. Now the orange ones are spatial spectra. They are k to the minus something, and the blue ones are frequency spectra. They are omega to the minus something. Okay, they are k to the minus alpha and omega to the minus beta. Okay, so you see, you start with 3.5, you get these blue things which are all over the place. You go from even something, say, smaller than 2 to something almost close to 5, right? This is all over the place. Now, with time, you see at least the spatial spectra are coming down to a reasonable, not so bad range. And there are quite a few points which have actually converged here, okay, which is about a value of minus 4. Okay. So you want to do a theory of this problem? There's not even a number to get a theory out of, right? Now, there was a theory of this kind of by Fuchsot and Lebedev, who said that the exponent should be anything higher than 3. So that's this. I mean, I don't know. Anyhow, so this is a mess, right? And we are trying to understand this. But in usual inertial turbulence, if you look at the frequency, wave number spectra and the frequency spectra, you translate between them by what is called Taylor hypothesis. You basically say omega goes as k, and then I can relate alpha with beta, right? So let's look carefully at Taylor hypothesis. I will first start with some data. So we have done 3 sets of simulations. First one is a channel. The second one is first one is homogeneous and isotropic elastic turbulence. Second one is channel. And the third one is a jet. Okay. In each of the cases, I plot the Ek in the upper part, and I plot the E omega in the lower part. And I have also put some other data by other people in the same plots. Okay. You can see that in the first top 3, you can imagine some k to the minus 4. In the first one, the scaling is not too bad. The other 2, you have to be very kind to me to assume that there is a scaling. Okay. But I am among friends, not among second reviewer. And now, if you look at the frequency range, even if you are kind, you would see that there are different frequencies coming up here. There is omega to the minus 4, there is omega to the minus 2, there is omega to the minus 3. And it's not only our data, it is also other people's data. So the idea is to try to make some sense out of this mess. And then
yes. The previous this slide. So what are the Marco Rosti has done simulations.
These are actually our
isotropic
yes.
elastic turbulence.
That's
the Lelop work. Isn't that channel flow?
Yes. So that one is the middle one.
Yeah, extremely non-isotropic.
Yes. So the first one is homogeneous isotropic. The second one is channel.
Yeah.
So that is our channel simulation with Marco.
Okay.
And the black ones are our simulation, and these orange ones are Lelep simulation. And then there's jet. So I'm putting all 3 of them here. Yes. Sorry. So it's a rectangular channel, and it is being pushed by pressure from left to the right, let's say. That's it. So jet is like it opens up like this. So the channel has two closed boundaries. So two closed boundaries, one periodic boundary and one long, say, streamwise direction. The jet is coming out from this and going out like a cone. Okay. I will almost not talk about the jet. I will talk mostly about the channel, and about the isotropic simulations. Okay, but we start, yes.
You're mixing up a lot of different boundary conditions.
Yes, but not really mixing up. I'm keeping them all in three separate plots. So this is homogeneous isotropic, which we call box. The second one is channel, third one is jet. And this is the box, the K domain, the K spectra and the omega spectra. So the K spectra we take by looking at a picture and then Fourier transforming in space and then averaging over many snapshots. The omega spectra we take by taking the time series at one point and then Fourier transforming in time. So that's the one we do in all of these cases. Yes, please.
You have all those blue symbols.
Yes.
They are for these three different cases.
So they are, yes, but they are different simulations, experiment, and so on.
Yeah, but are they all over the place for the jet?
That's a good question. So even if for the same geometry, it's clear that your frequency spectra and K spectra can be different, even at the same geometry. For example, if you look at this one, they are both channel geometry. One is a frequency spectra measured at one point. The other is a spatial spectra measured by spatial Fourier transform. You could call K to the minus 4, and you get what you could call omega to the minus 2. So in that sense, even in the same geometry, you can get two very different things. And over here, what I would like to think is that the frequency spectra is much more spread. The spatial spectra is not that much. And with time actually is coming closer and closer to a reasonable agreed value of minus 4. There are several simulations which are actually on this one point, not only our simulation. Okay. So we come to Taylor hypothesis. Okay. But not exactly this one, a slightly different one. So the idea is that if the intensity of a turbulent velocity fluctuation u is small compared to the mean flow speed, then the temporal response of the flow at a fixed point in space can be seen as a result of an unchanging spatial pattern. So it basically means you are sitting here, you have a probe, and your flow is going past you. Okay. And the fluctuations in the flow are small compared to the mean velocity. So what you get is basically a spatial spectrum. So that means your space and time are related to each other in a linear way. You could say omega, your frequency goes as some velocity times k. So you could say if omega goes as k to the power z, then there is a dynamic exponent z equal to 1, which will lead to, in the language I was talking before, alpha equal to beta. So there will be k to the minus 5/3 in space and k to the minus 5/3 in time, or rather k to the minus 5/3 in wave number and k to the minus 5/3 in frequency. This is old hypothesis of G.I. Taylor, has been used to analyze almost all data in grid turbulence. It is on extremely firm basis, but it is also known that how it can go wrong in inertial flows. For example, if there are coherent structures in the flow, you have to be careful. If you are trying to calculate higher order moments from this data, you have to be careful. All of that has been studied in great detail over time. Okay. But now, given that we don't want to do very difficult calculations. Let's have kind of a qualitative look at the Taylor hypothesis. Okay. And to begin with, I am just writing the Navier-Stokes equation. Okay. And I use the picture of turbulence that a velocity small u at a scale r goes as r to the power h. If it is Kolmogorov, this h would be 1/3. Okay. So u by capital U goes as r by capital L to the 1/3. Okay. That's easy. Now let's do something as simple as dimensional analysis. So the first term is u by time. The second one, you could imagine, will break up in two parts. Because if you are thinking about a channel, you have a mean flow in the channel. So you could say there is a mean flow advecting it, and there is a fluctuating flow at the same scale that is advecting it. So this term could be something like capital U, U by R, and then U square by R. And in the right-hand side, you will have viscosity, nu by R square, okay, just by dimensional analysis. I am dropping the pressure because in principle, I can just, because it is divergence U equal to 0 in compressible flows, I can just project the pressure out, okay? So, okay, slight massaging by putting in the length scale. So I multiply by L, the large scale, divide by U. I get Lu by L by Ut, L by R, Lu by Ur, and the L nu by Ur square. Okay, just simplify it a little bit. You can see, so I defined a time scale capital T, which is capital L by capital U. So the first term is capital T by small t. The next one is capital L by small r. The next one is capital L by small r to the 1 minus h. Because this u goes as r to the h. This is r, this is 1 minus h. And this goes as r square. Turn it around to find your time scale. You get r by L to the 2/3, and Reynolds times r square by L square. Okay. Now take the limit Reynolds going to very large. The last one is the largest. That means it is the slowest time of decay. So if you ask what is the time scale over which an eddy of size r is going to change, this is going to be a very, very long one. You are never going to show up. Then among the two, r by L and r by L to the 2/3, at small r, this is the fastest. And that means that is the smallest scale. So you will get t going as r to the power z, which will give you dynamic exponent z equal to 1. Now, if this behavior of the Taylor thing, where you see that you have dynamic exponent z equal to 1, is also called sweeping. It basically means there is this large scale velocity capital U, which is sweeping your small scale flow past you. Okay. Now you can imagine when I look at this problem, I want to remove sweeping. You want to remove sweeping, you can put a particle in the flow and then follow the flow from that particle. That would be a Lagrangian and quasi-Lagrangian picture of the flow. If you do that and remove the sweeping, you will get an exponent of 2/3, which is exactly what you will get if you use Kolmogorov-like dimensional argument. Okay, that's what happens in inertial turbulence. And if you play the same game in elastic turbulence, then you will come to a very different place. Now in elastic turbulence, you can show that this exponent h is actually 1. So you get L by r to the power 0. So time and length are actually not related to each other at all. You will end up with 3 different dynamic exponents, none of which are going to be clear. More importantly, you cannot also take the limit Reynolds number going to infinity, because elastic turbulence is when viscosity is very much present into the problem. There will be no one dynamic scaling. There are going to be many different dynamic scaling exponents. This I haven't shown here. This I have left for the afternoon. Okay, but what about the data? So if there is one dynamic scaling exponent, what would the data look like? And what would it look like if there are not one dynamic scaling exponent? So this is my channel. I define a correlation function, which is ux at x and x plus r, where r I take along the streamwise direction. And between, let's say the flow is from left to the right, I look at 2 points along the flow, x and x plus r. And I look at the x component of velocity and the y component of velocity. This gives me 2 correlation functions, cxx and cxy. And then I can divide them by their values at 0, and I can get gxx and gxy. So in the top part, I am plotting that as a function of r and t. Okay. You see the contours, they are all making an angle between r and t. They all look like straight lines, which is basically telling you r is proportional to t, and the exponent between them is 1. Okay. So you can take a cut along it, and you can get the gxy for different values of r as a function of time. Then if you scale time, so that time goes as r to the power 1, all of these curves are going to fall into one universal curve. And then over here, you find r going as t, and you get a perfectly linear behavior. This is the essence of Taylor hypothesis, that what your space-time correlation functions, they all collapse if you scale time in an appropriate way with length with a dynamic exponent of 1. Now, what happens in elastic turbulence? Your contours are completely different. They are not making any angle at all. And if you look, take a cut through them, and if you look at what it looks like, you get something quite strange. You see that if you are looking at gxy, then they more or less come on a straight line. But if you look at gxy, they are not there at all. So there is not one dynamic scaling exponent. Different quantities are behaving differently. If you take this plot, for example, and I really want to get this point across. So let's say this is my correlation function plotted at different values of r as a function of time. Now I want to scale time, okay? So if you look, these black points are the peak of my correlation function. And another set of black points is where I have defined, see the correlation function, the highest value is 1, right? So I have marked, over here you can see I have marked the value 1 by the black dots. And some fraction of that by the blue points, okay? So you can try to collapse it so that all the black points fall on each other. And in the inertial turbulent, you find all the blue points also immediately fall on each other. And they all come together in this one line. In the elastic turbulence, your black points follow one scaling, your blue points follow something else, which is not scaling at all. There is no way this whole function is going to collapse. There is no one-time scale into the problem that is related to length scale, which is essentially saying there is no one dynamic exponent. The Taylor hypothesis in elastic turbulence is fundamentally broken. Okay, so that brings me to the first summary. So in elastic turbulence, the Taylor's frozen flow hypothesis doesn't hold. And this is because the nonlinear advection is absent. See, the clue to Taylor hypothesis is the nonlinear advection term. And that's the term which is either absent or subdominant in this problem. Now, even in inertial turbulence, you need to be careful applying the hypothesis because there are coherent structures and so on. But this is something different. This is something fundamentally different. Here it is fundamentally wrong. There is no obvious dynamic exponent. Now, this brings us to another case, and this maybe is of some interest to the community. So the elastic turbulence, people have thought of it as weak turbulence in the sense of elastic waves. So if you, I think the community here knows Alfvén waves. And typically when I talk to non-plasma people, I tell them that Alfvén waves are like waves on a violin string. You have a string and you perturb it and the Alfvén waves go. Now, let me be that crude with you, and you know it is more subtle than that, but for the moment, now you can imagine that all the polymers have lined up. So that's like your violin string. And then you can imagine that there can be a wave propagating along it. But anyone who has done a Alfvén wave analysis knows that there is no Alfvén wave without the nonlinear advection. One part of the Alfvén wave is the linearized advection. If advection is absent, there are not going to be elastic waves in this problem. And the understanding of elastic turbulence is not going to come from weak turbulence of elastic waves. At least that's what we think now. Now, Victor has recently done experiments trying to look for wave-like behavior, and he has calculated exactly this quantity, which does show a linear wave-like behavior, because in waves like sound waves, omega goes as k, so z equal to 1. But what we find is that one quantity may behave that way, but other quantities may not. The other thing that we know is that if in the simulations, we can completely throw away the advection term, and we still get the exactly same k to the minus 4. So it's clear that you can get k to the minus 4 without any kind of wave-like, elastic Alfvén wave-like behavior in this problem. So what gives rise to elastic turbulence? I don't know. At the moment, it's an open problem.
Or you say that if you were to increase the one number, you would not smoothly transition to homogeneous turbulence.
No, if I go down, no, I'm not saying that, because see, I am already in low Reynolds number. So if I go down in Deborah number, I will come to laminar flow.
Just at the limit, there's a small amount of polymers. Your Taylor hypothesis, or would you do a smooth transition, or you have something very different?
I think at least in geometries like channels or other ones, people have shown that if you are in small Reynolds, zero Reynolds number, there can be elastic instability that make it unstable. And these are linear instabilities. So there is a boundary, so to say. But you remind me maybe of something else. So there is a large footprint of Dagen on polymeric turbulence. I don't know if, yes. And one of the things he commented on was that there is a smallest polymer concentration above which polymeric turbulence kicks in, which I think there is enough evidence to show that that may not be true. But you are not coming in from that direction. Okay, because see, often happens is that there is this expression in English called bee in the bonnet. I don't know if you know that. Bonnet is like a large hat, and if you get a bee trapped inside it, it will kind of all the time, right? So it happens to all of us that we think of a problem, someone asks a question, but you have your favorite complaint. So you always land up there. So I don't know if you are going that way.
With a little amount, an infinitesimal amount of elasticity in the problem, it just totally wins, for instance, the Taylor hypothesis, which you seem to be saying it is true.
No, I
don't have elasticity.
No, I think the important thing is whether you have the nonlinear advective term or not.
Reynolds number is small.
Yes, or zero.
Then the Taylor hypothesis won't. Don't have them much carried around.
That's exactly is the point. Yes. Yes.
Could you comment on the dispersion properties of the elastic waves? You're making an analogy with how.
So it's assumed that they are linear. Omega goes as k.
Well, then, so are we heading down the road then the only way you get an interaction is by counterpropagating waves?
That was in the picture, yes, in the elastic waves. But I don't think that is true. I don't think there are that kind of elastic waves. But if you also look at the last line, so Mike talked about these nonlinear traveling waves, which are fundamentally very, very different kind of waves. Now, can similar waves be present and interact to give me elastic turbulence? I don't know, but those waves are all there in presence of the nonlinear advection.
There are certainly instabilities, linear instabilities. It's
Yes.
zero Reynolds number in channel flow that lead to nonlinear traveling waves that are analogous to what I talked about.
Exactly.
It's a different family of waves that are dominant.
Exactly. And whether they can come to give me elastic turbulence, I don't know. But if it is, these are very complicated dispersion relations.
Question remains of how you use the spectrum, say.
The spectra is open.
Would like to make a comment on the second point, the nonlinear advection term, what you're saying is subdominant or absent. Recently, we did some work in terms of shear flow, looking at the Taylor hypothesis. In fact, what we're looking at is the correlation between the Eulerian acceleration, so the UDT, partial derivative, and this nonlinear advection term. And when they are uncorrelated or very strongly correlated or anti-correlated, then you can conclude, in fact, that the Taylor hypothesis holds or does not hold. So my question is, did you look at the correlation between the Eulerian acceleration and this convective acceleration?
No,
Because
we
there is
didn't.
maybe something would be
Definitely, we
worthwhile to
can
look
look
at.
at. We didn't look at acceleration. We looked at exactly this quantity, which is the correlation function of velocity. And then we made their space-time plots, and we showed that you cannot collapse them. There is no one exponent that collapses them.
So relatedly,
Yes.
in some of the simulations at least, you see elastic turbulence where the Reynolds number is just zero. There's just absolutely not.
A really good question.
Yes.
Yes.
There's just not a convection.
So we have done that by just throwing away the nonlinear advection. Okay, how much time do I have? Oh, wonderful. Okay, how much time do you have? Okay, so now that's say part one of the story. Okay, so this is the more recent one. What I'm going to talk about now is a slightly older story. So what I told you about the Taylor hypothesis and so on is not published. So mum is the word. But this is definitely published. So now what we are doing is we are doing simulations of homogeneous isotropic elastic turbulence, and we are slowly increasing our Deborah number at a very small Reynolds number. So when now you see Mike talked about Weisenberg number and I am talking about Deborah number. They are very similar quantities. They both have the polymer timescale in the numerator and some flow timescale in the denominator. Typically, if you use small scale flow timescale, it is called the Weisenberg number. And if you use large scale flow timescale, it's called the Deborah number. Typically, but not always. So when you look at papers, just check exactly what they're defining. So for me, this Deborah number is defined with respect to large scale. So as you know, in turbulence, there are eddies of different time scales. And there is the eddy, which is the slowest, which goes over the whole box. And the typical time scale of this is called the large eddy turnover time. So in my unit, that time is 1. So a Deborah number of 1 means that the polymeric time scale matches the largest time scale in the flow. Okay. So I'm increasing my Deborah number. Now over here, you see there is a Newtonian flow which has no polymers in it. And this is a forced flow at a high Reynolds number. So you don't see anything interesting. You just see something that calls up very fast exponentially. And now as you increase the Deborah number, go to 1/9, 1/3, and once 9, you get a reasonably good spectra. Okay. And this spectra is almost a decade. You can fit things. You can find a reasonably good power law. And then over here, you can see there are several things being plotted together. There are simulations of different sizes, 512 cube, 1024 cube. And there are simulations with different forcing. One is by the scheme given by Pope. One is called the ABC forcing. There are different models of polymers, Oldroyd B and Fene P. And there is one simulation where the advective nonlinearity has been thrown away. But all of this falls into a k to the minus 4. So it is reasonable to assume that k to the minus 4 is probably somewhere close to truth. Okay. At the same time, you can find out the spectra of the polymer. So that is a little bit tricky thing. So if you remember Mike's talk, so what gives the what describes a polymer is the end-to-end distance, right? That's a vector. Now you remember Mike took that vector, again to take a direct product of the vector with itself. Then he got this tensor C alpha beta. Actually, not completely true. He took a direct product of the vector with itself and then averaged it over the thermal noise to produce this tensor C alpha beta. And then the equations you write are the equations for that tensor, okay? But you can demand that given that it is a symmetric tensor, what is its square root? And a symmetric tensor has a unique square root if you assume that the square root is also going to be symmetric, okay? This is described, this formalism is described in a beautiful paper by Charlie Doyle. If you do that, then you can often turn your polymer, what we call polymeric spectra, is like the second order quantity in this quantity B. And then you calculate the two spectra. One of them is k to the minus 4. The other one has a much smaller scaling range. If at all, this looks like k to the minus 2, k to the minus 3 by 2. So you could say the kinetic energy goes as k to the minus xi with xi equal to 4. And the polymeric thing goes as k to the minus chi with chi equal to 3/2. Okay, that's kind of what the picture is. Yes, please. No.
Is that like, do you have a reason to expect forward cascade without?
There is, in some sense, there is no cascade. Because you see, viscosity is important at every scale. So more because I don't want to disturb the small scales. In the experiment, you can imagine that the thing is being driven at large scales. So it's...
If you have a bigger experiment.
But you're still driving it from the boundaries, which is large scale. If you want to drive it at small scales, you need to do something else, right? You can put bacteria in it.
To understand the physics of whatever this power law.
Right, but the thing is, typically the way we like to think that there are cascades, right? Here you cannot think of a cascade. So what I will try to make an attempt, then stay with me for a moment. So I go, I mean, of course, a turbulence person always falls back to whatever they know. So what I do is I look at the equation and I look at the contribution from each term and calculate what are called basically integrate, because this is homogeneous isotropic, integrate over k, and look at how each of these terms work. So Prasad talked about this, remember, he talked about fluxes and transfers. And you can see that there will be three contributions. One from the nonlinear term in the Navier-Stokes, which is this pi, one from viscous dissipation, and one from polymers. And if you plot them, you see that the nonlinear term is practically zero. It's very small. If it was inertial turbulence, then it is this term which would have been large and would be constant as a function of k. And that would be the clue to Kolmogorov. But what you find is what you actually need to balance are the slopes of this, because these are cumulative terms. You see the slope of the polymeric contribution balance the slope of the dissipative one. So if you do that, then you say, look, here is my polymeric contribution, which is the strain, which is the strain S alpha beta multiplied by the viscosity of the flow, which balances this polymer term. These two terms balances each other. If you do that, then you will get a relation between xi and chi, that xi is equal to 2 chi plus 1. I'm not going through all the steps. We can do that in the afternoon. But I guess you can see how it goes. You assume that there is a scaling exponent, put that behavior in the terms, match it, and you will get a relation between H and B, which will give you a relation between xi and chi. And you get xi equal to 2 chi plus 1, which is actually satisfied by our simulations. So not too bad. That basically tells you if you know one of them, you can tell the other. Okay. But at the moment, I don't know either of them. Okay. It's known up to that point. Okay. But there is a bigger mess waiting for you. So all these exponents are higher than -3. So there is this very standard thing in turbulence that we always do in our head, which will say that, look, there is the structure function and there is the energy spectrum. One is Fourier transform of the other. The structure function scale as r to the power 2/3. Then how would the energy scale? It's easy. You turn the minus sign and then subtract 1. Okay, 2/3 minus 2/3 minus 1 minus 5/3. Okay, very easy. And if you go from Fourier to real, it's just the other way around. Okay, so if you start from k to the minus 3, change the sign, you get 3, add 1, you get 4. All well and good, but something very tricky is going to happen. So let's look at the structure functions now. Okay, and let me tell you what happens in usual turbulence. In usual turbulence, structure functions at very small scale. If you want to ask how should the structure function behave at very small scale, see, structure functions are velocity difference to the power p, right? Now, if the scale is too small, velocity difference can just be Taylor expanded, right? So second order structure function will just go as r squared at very small scale. At higher scale, it can go as zeta2, which is the Kolmogorov number. So it's square and then 2/3. So, but you see the difficulty that if you Fourier transform and get something in elastic turbulence, for example, which is higher than 2, in the limit r going to 0, that one is never going to show up. This need to be appreciated. Okay, this is a tricky point. So let me just show you some old stuff. So on the left, there is a very nice paper by Schumacher, Srinivasan, and Yakut, who looked at structure functions of order 2n in turbulence. And then instead of looking at Kolmogorov, they looked at very small r and divide this by r to the power 2n. All of them goes to a constant, which means at small r, they just are Taylor expandable. They just go as r to the power 2n. The same is true about our data. So if you take the structure functions at different Deborah and plot them by r square and small r, they all go there. Okay, and even 2n approximately goes there. But what happens when you look at it between the real space and the Fourier space component? So if you say your Fourier space goes as k to the minus I, then the structure functions will go as r cube. That r cube is subdominant to r square, right? And if you go to the limit r going to 0, nothing is going to show up. In inertial turbulence, you could tune your viscosity to change the scale where the inertia matters. Here, there is nothing to tune. So how to extract these subleading exponents? You see, the leading order term is always going to be r square. There is an r cube which is hiding, and you can't find that. So the way to do that is to, instead of calculating usual structure function, you calculate a structure function one step ahead and one step back, so that you cancel the linear contribution term. Okay, so you do a new kind of second difference of velocity, which is ux plus r plus ux minus r minus 2 times ur. And you calculate the structure functions of these quantities. And they do show up and they give you r cubed. Actually, they give you something more. If you now calculate the pth order structure functions, you see they're actually intermittent. They're falling on a different, they start on a different straight line, which is 3p by 2, not the Kolmogorov p by 3, but they do depart from it. And so there is intermittency in elastic turbulence too, as it looks to us. And now I'm going to tell you an absolute secret. As far as we know, if you take away the nonlinear term, the k to the minus 4 exists, but the intermittency goes away. So the intermittency may be a small Reynolds number effect, which we don't know. Even the k to the minus 4, we don't know. So this is really an invitation to elastic turbulence. Okay, so to summarize, Taylor frozen flow hypothesis does not hold in elastic turbulence. So be careful in interpreting the temporal spectra. The non-trivial scaling of elastic turbulence is revealed by the second difference of velocity. Elastic turbulence is intermittent. There is evidence from structure functions, probability distribution functions, kurtosis. I haven't shown you all the evidences. And there is this idea that the dissipation of kinetic energy is intermittent, but the Kramer function is different. I haven't explained any of that, so feel free to ignore. But some of the other people may ask questions, so it's for them. But thank you very much for your time and your patience.